Related rate problems. Some of these ones have quite a few views. So here's the idea in a related rate problem. You're given the rate of change of one thing and usually asked to find the rate of change of another thing. So, for example, we'll have a problem later on with a snowball. And as time changes, the snowball melts. So what's changing is the surface area is changing, the volume is changing, and the radius is changing. So at a certain time, if the surface area is changing at minus 1 centimeter squared per second, how fast are the other ones changing?
Could you even apply a radius if it's perfect?
Well, if it stays perfectly spherical, if it's like spinning in the air so that it melts nice and symmetrical,
Theoretically.
we're doing some theoretical questions. Okay? So in order to do this, we're going to need to find an equation that relates the two variables that we know are changing with respect to time, and then use the chain rule and implicit differentiation to differentiate both sides. So what does that look like? Well, here's a question. How fast is the area of a circle increasing at the moment its radius is 100 meters and it's increasing at a rate of 2 meters per minute? So this, where could we see a real life of this example? Well, you have a circle increasing. So if you dropped a marble into a pool, it drops and then a circle ripple goes out. Okay? Now, this example is a little bit of a huge extension of this because the radius is at 100 meters. I don't know how big, maybe you'd have to drop an asteroid into the ocean in order to have it continue. But if you would do that, I'm not sure that it would travel only at 2 meters per minute. That seems really slow. It's only going to go this far in a minute, but it's already that big. So I'm not sure how you would create a ripple effect in the water to do that, but as far as the numbers don't matter, but that could be a situation where this is happening. You do drop a pebble into a pond, it creates a circle, that ripple extends. That ripple might be extending at a constant speed. In this case, the rate is 2 meters per minute, and you want to figure out how much is the area changing. How fast is the area changing at a certain moment? So in order to get the setup for this question, the fact that they're telling us, there you go, it's all up there. The fact that the area is changing with respect to time and the radius is changing with respect to time means that both area and radius are functions of time. But we don't know what those equations are, and we won't figure them out. But we're told that area changes with time and radius changes with time. That means there exists some function area in terms of time. There exists some function radius in terms of time. We want to find how fast is the area with respect to time changing. So this is our variable or thing we want to discover. We know that the radius changes with respect to time at a rate of 2 meters per minute. And not only do we know that it changes at 2 meters per minute, we want to find the area with respect to time at a specific time or a specific moment when the radius is 100 meters. This is just the background information. And this is important background information. With all of this background information, we now have to try and say, can we create an equation that relates area to radius for a circle? Well, this is one that you know quite well. What's your formula for area of a circle? Pi r squared. So we have an equation that relates area to radius. Are there any t's in that equation? None. And yet, we can still take the derivative with respect to time of this. And the reason, so this is what we're going to do, this whole equation, we're going to take the derivative with respect to time of it. And the reason we can do that is because area is a function of time, even though we don't know what it is. And radius is a function of time, even though we don't know what it is. Yes? You could write area as a function of time equals pi radius as a function of time squared. Okay? You will find that that notation probably causes you more headaches than the regular notation. Okay? So what happens and how do we take the derivative? Well, this is where implicit differentiation comes into play. If I want to take the derivative of a, it's just going to be 1. You can write 1 if you like. You don't have to write 1. Times by chain rule, this is implicit differentiation, dA dt. On the other side, what's the derivative of pi r squared? Well, the 2 would come out in front, pi r, and then the inside function is r. What's the derivative of r? dr dt. This is our implicit differentiation that we've done before. If we want to take implicit differentiation and say, well, what do you do without any meaning? Implicit differentiation says, do your derivatives like normal. Derivative of a is 1. Derivative of pi r squared would be 2 pi r. And then after you do the derivative of a variable that's different than the variable you're using, you have to write dA dt. After this one, you'd have to write dr dt. And now we want to find, this is what we want to find. We want to find dA dt when the radius is 100, and we know that the rate of change with the radius is 2 meters per minute. So we can now just substitute everything in. dA dt, which is what we want to find, is equal to 2 pi. We want to find it when the radius is 100, and we know from the question that the radius is changing at 2 meters per minute. So we can plug all of those values in. Multiply this out, we'll get 400 pi. Our units were meters, so it'll be meters squared per minute. Because area's units is meters, meters squared, times unit is going to be in minutes. So this circle that's traveling at 2 meters per minute, at the moment it reaches 100 meters, is changing at a rate of 400 pi meters squared per minute, which is roughly 1,200 meters squared per minute. If you know how big a meter squared is, it's 1 meter by 1 meter. Imagine 1,200 of those. It's increasing its area quickly. Okay? So where are other examples of these circles expanding and you're wanting to figure out things like this? You could think of atomic bombs. When they go off, they expand circular from where they exploded. And they go a little bit faster than 2 meters per minute. Okay? Yeah. It would be nice if it traveled that slow, but you can figure out at a certain point how much damage is happening at certain times or at certain. So we do have many examples where circles increase, and this just shows us how we can figure out.
How about black holes?
Black holes.
Or reverse nuclear bombs where you unexplode stuff, where you build stuff together. Does that work?
So here we have a balloon 30 centimeters in diameter and being inflated such that its radius increases at a rate of 3 centimeters per second. And we are going to assume in this case, I should probably have put spherical, because I don't know the actual equation for a balloon. So we're going to assume that the balloon is spherical. and it's being inflated so that its radius is increasing at 3 centimeters per second. Okay? How fast is the surface area of the balloon increasing? So a couple of things as far as the setup. We want to find how fast the surface area is increasing. So I'm going to call my surface area capital S. This is what we want to find. If we're trying to find ds dt, that means that surface area is a function of time, even though we won't be able to find that equation. What do we know? We know that radius is increasing at a rate of 3 centimeters per second. So that means that radius is also a function of time. The radius. And in particular, we want to find how fast the surface area is when the radius is 15, because the diameter is at 30. So here's our setup, and now we need to know our surface area of a sphere formula in terms of the radius. What is it? Do you know your surface area of a sphere formula? 4 pi r squared, yes. Okay. Do you know your volume? Do you know your volume of a sphere formula? Because you'll need that one too.
Is that 4 pi over 3? Or no, 4 pi r 3 something.
4/3 pi r cubed. Okay?
I was trying to say.
Those are your spherical formulas. If you know one of them, I will tell you you know the other one. Because if you take the derivative of the volume, you get the surface area. I don't know. Let's see. What happens if you take the derivative of a circle? You get circumference. Whoa. You move down 3 dimensions down to 2 dimensions, 2 dimensions down to 1 dimension. Isn't that interesting? Now, I remember the surface area of a sphere the following way. Okay? I imagine a sphere, and I imagine looking at that sphere. What shape do I see? Well, I see a sphere because 3 dimensions. But if I was thinking 2 dimensions, what I see a circle. Okay? And if I imagine seeing the circle from this side, there would be one circle, but I wouldn't see the circle from this side. So I imagine seeing the circle from that side. And if I see 2 of those circles, that would be the same as a flat disk. If I want to see the sphere in 3 dimensions, I'd also have to look at it from the top and similarly look at it from the bottom. And so I'd see a circle from one side, a circle from the back side, a circle from the top, and a circle from the bottom, or surface area being 4 circles. 4 pi r squared. So whether that theoretically works or not,
Kind of just like skip out on left and right.
well, left and right are kind of covered by the up and down when it, like,
But you could also say that up and down is covered by left and right. By it's not great.
it's not great, no. Okay? You could do front and back, left and right, and then not do the up and down, but that's the way that I visualize it. And whether that theoretically works or not, it does get the right formula. 4 circles, 1 sphere, surface area of 1 sphere, surface area, not volume, right? Surface area of 1 sphere is 4 circles. And however way that you look at it, it's a nice way to help you remember the formula. So now we have we have our formula, surface area is 4 pi r squared. So now we want to take the derivative with respect to time of this formula. Well, we're going to get ds dt. Derivative of this side, the 2 would come out in front. Subtract 1 from the exponent, multiplied by dr dt. So there's our implicit differentiation.
Wait, so the ds just kind of just went with the...
Well, the derivative of s would be 1. But then chain rule would say, well, what's the derivative of the inside? That's ds dt. So we want to find ds dt when, this is what we wanted to find, when the radius was 15, and we know that dr dt was 3 centimeters per second. Multiplying these out, what do we get? 360 pi.
Beautiful.
And this is going to be, surface area is in centimeters squared per, it's time in seconds. Make sure we get all of our units right, and yes. So the surface area at that moment is increasing at 360 pi centimeters per second. So we could have done a volume question. If you wanted the balloon to have its radius increase at a constant rate, how much air would you have to be pumping into it? Like you'd have to put more and more air in as you went because the volume would increase at a faster rate. Now in this unit I have got, yes, so I'll stop the video here so we separate it into chunks.